So next let us discuss what is the Laplace transform of unit step function. So before that you should know what is a unit step function. Unit step function, what is this? This is defined on, this is of unit magnitude and it is a step function. That means whenever it is greater than 0, its value is equal to 1, and whenever it is less than 1, its value is equal to 0. So this is your given function. Okay. So what is the formula, the mathematical expression? So u of t is equal to 0 whenever t is less than 0, and it is equal to 1 whenever t is greater than equal to 0. Where 0 is the point of discontinuity, because here from the left hand side its value is 0, from the right hand side its value is 1. So they are not equal at this point, therefore we can write this to be the unit step function u of t. It is also denoted by u0t. 0 represents we have discontinuity at the point 0 here. Okay. So next let me define this. The 0 corresponds to this point. So next let me define its translation. So suppose I am defining this function u of t minus a, or in other words you could also write it to be uat. So that means we have now shifted this function a distance to the right hand side. So it would be 0 whenever t is less than a, and it would be 1 whenever t is greater than equal to 0. So this is the unit step function, and it is defined like this. So suppose this is the point A, so after A its value is 1, so this is 1, so this is 1, and it is equal to 0 whenever it is less than A. So this is the unit step function. Why this unit step function is so important to study? Because in various situations when you have on and off conditions, so that means you say there you apply this function. So whenever you want your signal or anything to be on, so at that point we say okay, put that or place that to point 0, or I want after a units or time or whatever, I want the function to be on to get started, otherwise I want this to be off. So I multiply this by unit step function. So that is the utility of this function. So we are saying after a units we are switching on the device. So that is the utility of this unit step function. Moreover, you could also multiply the given unit step function by some other function. So suppose you have some function f of t as sin t. What is this? The sinusoidal wave, defined like this. So this point is 0, this point is pi, this point is 2 pi. So it would be something like this, and it would be the same on the left hand side also, right? This point would be minus pi, this point would be minus 2 pi, and so on. And what is the unit step function? U of t minus 2. So this is equal to 0 whenever t is less than 0, and it is equal to 1 whenever t is greater than equal to 0. So it is like this. This point is 2, this magnitude is 1. So after 2 its value is equal to 1, and before 2 its value is equal to 0. So now what we are doing, we are multiplying this function with this function. So we have another function, new function, let me call that to be g of t. So g of t is this f of t multiplied by u of t minus 2. So how can I define this function? So it is defined like this. Whenever t is less than 2, its value should be 0 multiplied by sin t, so it is also 0. And whenever this t is greater than equal to 2, so its value is 1 multiplied by sin of t. So this is the new function, and how would it look now? So you see your function would now look like this. So this is unit 2. After unit 2, your function would be like this. So that would be the sine wave, and before this it would be 0. It would be 0. So that is the utility of this function, that after this point 2 your curve would start to move again. So this is the function g of t. So next thing is we have to define what is the Laplace transform of this unit step function. So to define the Laplace transform of unit step function, we will first define the second shifting property. We will define the second shifting property. Now this is an important topic. It says that if ft be the given piecewise function, piecewise continuous function of exponential order and the Laplace transform of f of t, that is given to be capital F of s, then the Laplace transform of u of t minus a into g of or some function f of t minus a, you could call this to be g also, right. So this is e to the power minus as into capital F of s. So basically what you are saying? You are saying whenever it is e to the power minus as, so that is equal to that function shifted by a units to the right, and multiplied by this unit step function. So this is the second shifting property. This is very simple. So let us first see the proof. So let us see its proof. For the proof, we consider this quantity Laplace transform of u of t minus a into f of t minus a. This is equivalent to integration from 0 to infinity e to the power minus st u of t minus a f of t minus a dt. So we have to perform its integration. What is the definition of this function? This function is 0 whenever t is less than a and 1 whenever t is greater than equal to 1. So the integration now becomes 0 to a e to the power minus st, its value is 0 into f of t minus a dt, plus the integration from a to infinity 1 into e to the power minus st f of t minus a into dt. So now this quantity is 0, whole thing. So we will be left with this quantity. So here we would have integration from a to infinity e to the power minus st f of t minus a dt. Now we have to make it into the Laplace transform of something. So what would be this? So you could write this as you could replace the variable. So what you can do? You could substitute, put t minus a as x. So your dt would become dx, and whenever your t was a, what would be your x? X would be 0, and whenever your t was infinity, your x would be infinity. So now using this substitution, your integration would be from 0 to infinity e to the power minus s. Instead of t, you would write x plus a, x plus a, and then f of x dx. So this you could separate out these terms. So it would be e to the power minus s a outside this integration. Why? Because this does not contain x, and we are performing this integration here with respect to x. And what is this? This is nothing but the Laplace transform of s, f of x, right? Because by definition, you know what is Laplace transform of f of t. This is equal to integration from 0 to infinity e to the power minus st f t dt. So if you change the variable from this f of t, right, if you change this variable, so that won't make any effect. It would be again be integration from minus sx f of x dx. So this quantity is nothing but the Laplace transform of f of t. And what is this? This is e to the power minus sa into the Laplace transform of f of t, that is capital F of s. So this is the proof of this second shifting property. So in particular, suppose the given function is, suppose we wanted to calculate this. What is the Laplace transform of u of t minus a? So here if you compare this with the given shifting property, your f of t minus a, that is equal to 1. So your f of t minus a is equal to 1, and you know what is the Laplace transform of 1? That is equal to 1 upon s. So from here, what would be the Laplace transform of u of t minus a? So according to this property, it would be equal to e to the power minus as multiplied by the Laplace transform of f of t. And what is f of t? Laplace transform of f of t, that is equal to 1 by s, because f is nothing but 1. Therefore, we have e to the power minus as divided by s. So you treat this to be another formula for calculations. So this is one formula and this is one formula, and they are very important. So you should remember these formulas very nicely. And moreover, this is the Laplace transform of u of t minus a. Next formula is, what would be the Laplace transform of u of t? The Laplace transform of u of t, that is 1 by s. So this is another formula. Here we do not perform any kind of shifting, so this term is not present in the Laplace transform.